Yeah, now I'm recording too. Okay.
Okay, I'm recording and Sky's recording. Good. So we're all here and we can begin this interview that we plan to conduct. Sky, how should I address you? Do you prefer to be called Sky or Dr. Sky, or how should I address you?
No, just Sky. It's fine.
Very good. Now, Sky, I was hoping we'd start out with a little bit of your background, where you're from, how you started to get interested in science, and sort of a little bit there about your background, if you could.
Yeah, sure. I was born in Greece and grew up in Germany after the age of 7. And my father introduced me to the solar system when I was 6 or something. And so I got interested in that. And I also watched a lot of Star Trek. And that's how half of the physicists get into physics. Yeah, and when I started reading about it more seriously when I was 17, yeah, 17, I think. Yeah, then I developed my own theory about how it all works after a few years. I especially had this idea about quantum mechanics being based on not the particles being fuzzy and in many places, but the observer being in many different worlds simultaneously. Not worlds where you do different things, but the worlds that are indistinguishable at the moment. Yeah. So I call that the similar worlds interpretation.
I'm sorry, you called it what there?
The similar worlds interpretation.
Okay, very good. Now, is that at a certain point you began to write a book about some of these theories and some of these findings of yours? Now, is that finding the similar world interpretation? Is that in the book that you've written?
Yeah, sure. That's the book, and this interpretation is kind of on the ground level, like the first step of everything.
Uh-huh.
Yeah.
And when did you write that book that you were holding up there?
The first version was published in 2014, but at that time it was very thin, like 50 pages, and now it's like almost 700 pages, 680 pages.
Could you hold the cover up just so we can see it again? And the complete guide to quantum gravity. Okay, good.
Yeah,
good,
the name changed a little bit.
The old one was quantum. What was it? Quantum gravity.
Quantum gravity and the role of consciousness in physics. Yeah, Jesse has written me since many years. I think since 2019 or 20.
That was what 480 pages.
Ah, yeah, you remember that better. Yeah, maybe.
So there's
right now it's like 700.
Yeah, 680.
Pretty impressive.
Where can people get that book or buy a copy of that to read some of your work?
Yeah, on Amazon. Yeah.
Okay, right on Amazon. Good.
Yeah,
so we covered a little.
I can't get rid of the old versions because sometimes I would lose a phone number and then I cannot change the old version, and so I just republish it. So that happened to. Yeah.
But now, why was it that you thought to yourself, okay, I got one book out there on this, but I gotta revise it? Why the revision? What was it about the work that made you think, okay, I've got to put more into this and get a different publication out?
Well, research grows forever, and I'm not publishing different books. I'm just putting all my new research always into my original book.
And can you go into some of that new research that one might find in the new book?
Yeah, so the product I'm trying to make now, the material analyzer, it's based on the gravity part of this quantum gravity theory. So this quantum gravity theory is called space particle dualism theory, or short SPD. So that means that every particle has its own quantum of space, and that's a sphere which is proportional. The radius is proportional to the energy of the particle, and so it's quite common for quantum gravity theories to quantize space, because we know that space can be changed by gravity. In Einstein's theory, it's changed by gravity, and so it must consist of something. And so people quantize it, but other people always use the Planck length for the quanta of space, and I'm using rather large quanta of space.
What
and
is the
so-
size of the quanta that you're using?
Yeah,
Again,
so a resting electron would have a space quanta with a size of 10 to the power of minus 21 meters, which is very large compared to the Planck length, which would be 10 to the power of minus 35 meters.
well,
So
don't you use something called an elementary, what was it, elementary space or a,
yeah, elementary space. Yeah, although it's a surface, but then it's a complex number surface, so you could still call it space. Yeah, space could have any number of dimensions.
but you relate that to the size of the electron?
Um, so it originally it was like a black hole, the size of a black hole, basically, based on the energy, but that would be too small. They couldn't overlap. So it's basically a scaled up version. So it's scaled up according to the difference between the force, the strength of gravity and electromagnetism. So it's really big, and it grows. It can also, so when you reach a certain energy, it becomes bigger than the wavelength, and then you cannot probe smaller distances anymore. So the smallest distance you could explore, according to my theory, is 10 to the power of 8 times 10 to the power of minus 18, I think, yeah, meters. So that explains also why particle accelerators don't find any new particles anymore, because they're not anymore probing smaller distances. Because
The
the
elementary
element
space
space
is
become bigger and bigger, then you can't see anything smaller anymore.
the elementary space is a variable metric that you could use.
Yeah.
I mean, it's a variation.
Yeah, there can be any size. So when energy is very low, then it becomes smaller than the Planck length even, but then it becomes gravitationally ineffective. Yeah. Anyway, so according to Einstein, there's gravity is based on curved space, but according to my theory, it's differences in density of those space quanta. And so there's a background of space quanta, which is based on the vacuum fluctuations, the energy of the vacuum. So, but if you add an object to the vacuum, like this or any other object, it has a lot of charges in it. So the charges emit virtual photons, and the hypercharges, the quarks, emit gluons, virtual gluons. So you get even more virtual particles. So around an object, there's an even higher density of these elementary spaces. And so if everything can only move on elementary spaces, like it's a quanta of space, so everything has to move like zigzag on these elementary spaces. So then it's attracted to regions of space with more of these elementary space, of these space quanta. And so things get attracted. So that is gravity. And so in that picture, you don't need gravity to be an independent force. You don't need gravity particles. You don't need gravitons to intermediate gravity. It becomes a side effect of the strong force and of electromagnetism, but actually mainly only of the strong force, because in electromagnetism, the virtual particles, they only live for a short amount of time, and the farther they want to reach, the lower must be their energy, and at some point they would become smaller than the Planck length. So only has to reach about 40 meters, but the strong force itself interacting. So one virtual gluon creates another one and another one, so it can reach to infinity without becoming smaller. And so the gravity coming from the strong force, I call it chromogravity, because the strong force is described by chromodynamics. So
In
chromodynamics
SPD,
means that they use the concept of color, because 3 colors become white. So if you want to have 3 things that cancel out to 0, you can call it color, although it has nothing to do with color. So instead of plus and minus, two things canceling to zero, you have three things canceling to zero. And because that's so similar to colors, they call it color charge. But here we are not interested in the color aspects, but only on how many color charges are there, how many particles. So according to Newton, gravity depends on mass. According to Einstein, depends on energy, because mass and energy are the same thing basically. And I say they're both wrong, and in reality, gravity depends on the number of particles, and more specifically on the number of protons and neutrons.
So does
Very
that
good.
mean in SPP, if you had like a neutron star and it absorbs like thermal energy or something, it wouldn't increase its gravitational potential?
So according to let's start slowly. When I say gravity depends on the number of particles, it sounds almost the same like saying it depends on mass, because more particles means more mass, right? So a lot of laymen would have that question: how is that different? So the difference is that energy, there can be positive energies and negative energies, and one negative energy would be nuclear binding energy. And so nuclear binding energy actually reduces the mass. And so, for example, iron, this here, it has the most negative binding energy, and so its mass is reduced, but the number of particles is not reduced. And so that means there are more particles, more protons and neutrons per kilogram. And according to my theory, therefore more gravity per kilogram. So every material has its own gravitation constant. So that solves the big problem about the gravitation constant, because people try to measure it since 200 years. And since about 50 years, they're very good at measuring it. So there should be good results, but they're not. They still all disagree on the gravitation constant. Every measurement gives a new value, and people are very confused. And they think they might not measure well enough, but they already have very narrow error bars, standard deviations. So it solves the problem. I can predict very precisely, based on knowing what material they used in the experiment, I can predict very precisely what the gravitational constant was. And the chance for this to be a coincidence would be something like 1 in 10 to the power of 18. Like, it's infinitely small, basically. Yeah. Originally, my analysis of all the G values that were obtained was looking at a range of acceptable values, because there were a lot of crazy values in the 18th and 19th century, but some people were skeptical because I was excluding a lot of values. But then it turned out that if you just look at measurements from after 71, you get basically they all lie in the acceptable range, with just a few outside, but they have self-admittedly, they have low accuracy, very low accuracy. And some of them were not even really interested in measuring the gravitation constant, but mainly checking the inverse score law, basically, if there are any gravity anomalies with distance. So that was just, they just measured on the side. It was not the main thing. Yeah.
Jesse, you have another question about that, or?
Well, do you have anything at this point?
But to come to your neutron star comment, so neutron stars, my theory says about neutron
or just
stars,
any massive body, if it absorbs non-hadronic energy like thermal energy or photons, does it increase its
thermal energy
gravitational
does
field?
affect. So if you have a lot of thermal energy, you would have less gravity per kilogram, because energy is mass, but the number of particles is still the same. So you have more mass, but still the same number of particles, same gravity. So the gravity per kilogram would be less. but well, thermal energy doesn't really matter. It doesn't play much of a role because it's the effect on the total mass energy is so little. But what has a very big effect with planets already a little? Let's take Earth for an example. That's gravitational binding energy has a very big effect for Earth. Earth would be 10 to the power of 15 kilogram heavier if it was stretched out, if you stretch it out to infinity. Now that it is compact, it actually has some negative mass, 10 to the power 15 kilogram negative mass, you would say. But there's still a little compared to the total mass, which is 10 to the power of 24 kilogram.
And the negative mass comes from where?
From the binding energy, from the gravitational binding energy. And so that doesn't change the mass of Earth much, but when you look at neutron stars, they have 15 to 20% negative mass, basically this binding energy. Their mass is reduced, but their gravity is not reduced. So when you reduce the mass, but the number of particles is still the same, then you have more gravity per kilogram. So the gravitational constant of neutronium, the stuff that neutrons are made of, they're entirely made out of neutrons. So you could call that neutronium. I've heard that term once in Star Trek, where they have an impenetrable wall, a door, and they say, oh, it's made of neutronium. Doesn't help to fire lasers on it and anything. And the gravitational constant of black holes is even higher because they have 30% gravitational binding energy. And so if the gravity per kilogram is very high, you need less stuff to get the same gravity. And basically when we measure how much mass has the Earth, how much mass has the sun, how much mass has a black hole, we look at the effect it has, gravitational effect it has.
Get a discrepancy of how much between your value and the current
yeah, it
mass
changes
of
by quite a lot. So there's a gap between neutron stars and black holes. So there's one neutron star has 1 sun mass, the other has 1.1, and so on. And there's a gap between the lightest black hole is, I think, 3.3 sun masses. But you should already get a black hole at 2.5 sun masses. If the collapsing core of the star has 2.5 sun mass, you should already get a black hole. But there's an unexplained gap between neutron stars and black holes, a huge gap. And statistically, we have already seen enough neutron stars and black holes that there should not be a gap statistically here. So if you use my theory to translate the masses, then they move together. So neutron stars become a bit lighter, and black holes become a lot lighter. And so the gap, they move in a way that the gap is closed, and there's a statistically normal small gap, which is equal to the gaps between individual neutron stars and individual black holes.
Do black holes evaporate in that speed?
No, black holes, yeah, so Hawking was wrong about that. Black holes do not evaporate, because for black holes to evaporate, in the Hawking process, there are these, it pulls virtual particles apart through the tidal forces, and so it emits photons. But if that process would really happen, I mean, photons only carry away energy. They don't carry away gravity, because they don't have. In my theory, gravity depends on the number of protons and neutrons, and a photon is not a proton or neutron, so it doesn't carry away any energy, any gravity. So you couldn't shrink a black hole using Hawking radiation. There has also not been any evidence for Hawking radiation being an actual thing. But a black hole will have some radiation, because when a star collapses, it never becomes a true black hole because time almost stops close to the Schwarzschild radius, and so the collapse is never complete. So it's still a star. The black hole is still a star, still shining, but the light of the star is just infinitely redshifted, means stretched out, so you cannot really see the light, but it's still there. If you had a very big telescope, you could see it. Radio telescope.
So, how would how would that change the Einstein field equation?
Yeah, initially I thought I have to change the Einstein field equation, but at the end it becomes
Pretty the
totally
same.
obsolete actually, because the Einstein field equation is based on the energy tensor, and if gravity does not depend on energy, you don't need tensors. The Einstein field equations are only so complicated because gravity in Einstein's theory depends on energy, and that makes everything extremely complicated, because if it really depends on energy, then gravity itself has energy, and that creates more gravity, and then that
Right.
again has energy, and that creates more gravity, and becomes highly nonlinear, and you can actually not precisely calculate anything in general relativity. It's very nonlinear.
So right now, what you're doing is measuring G values of different elements in your lab, right?
Yeah. So using Cavendish experiments, where you have two source masses and two test masses, which are suspended on a beam and on the ceiling, and the source masses attract the test mass and make the beam twist a little bit, but then the torsion of the string pulls it back again. So you look at this oscillation, and in my experiment it took like 15 minutes and 51 seconds, and in Einstein's theory it would have taken 15 minutes and 49 seconds. So it's a tiny difference, and so there you can see that using Cavendish experiments to measure gravity is extremely difficult, and that's also why only after 71 it became more precise. So I prefer to measure gravity using free fall experiments. That's the free fall adapter up there, and I can measure time differences of 0.1 milliseconds, 0.0001 seconds.
Describe
And
your apparatus, maybe.
yeah, and so I have a lot of I use vending machine balls and put different masses inside. Yeah, or here the zinc filled with zinc, and yeah, various other spheres filled with various materials. And so, but it might it's the layman might not understand why different materials having different gravitational constant also means that they fall differently. So the reason for that is the following. When you calculate in Newton's theory, when you calculate free fall or escape velocity or anything, you have on the left side you have kinetic energy, and on the right side you have when you calculate free fall, kinetic energy and gravitational energy on the right side, and both have mass in them in Newton's theory, because in Newton's theory the thing that causes inertia and the thing that causes gravity is the same thing, namely mass. And so when you solve for the escape velocity, for example, you put the mass on the right side and cancels out because there's already mass there. But in my theory, there's no mass on the gravity side because it doesn't depend on gravity. And so it doesn't cancel out. But it balances out because there's a quark count or particle count And so you get a fixed ratio. When you get more particles, you get more higher quark count or higher particle count and higher mass, but the ratio stays the same. So you get a material specific ratio. And so the free fall acceleration depends on the material. And so, for example, for lead, here I have a lot of lead and here a lot of steel, stainless steel. So the for this height here, about 2 meters, the time difference is 0.3 milliseconds. Yeah, and for wood, I also have wood-filled spheres. For that, the time difference would be 0.4 milliseconds to 0.5 milliseconds if it's dry wood. Yeah, it depends a bit on the
Around
composition.
a half
It's
of
rich on calcium or not.
half of a millisecond.
Hmm?
But it comes up around a half a millisecond, basically. Jeremiah, do you have
Yeah.
any questions about what he's doing in the
No, I'm
lab?
just fascinated. I don't know if you have a few more questions or Sky,
Yes.
is there more you want to cover about where you're at with your work and
Yeah, so
and
so
how
the
the community could support and things like that?
yeah, so I'm doing a Kickstarter about a project, a material analyzer, and so that works by so these experiments they take a long time. Cavendish experiments take a long time, and you wouldn't want to analyze the composition of something by throwing it down. So what you want to do is use a scale and a balance. So this here is a high accuracy balance here, and this measures mass like in the classical balances they're independent of the local gravity. So if you have a balance on the mountaintop or at the beach, it will show the same value because gravity's increase, it increases on both sides, so it doesn't make any difference. And so this measures mass, and then this measures weight because this is a normal scale. So it presses more at the beach than at the mountaintop, but you can calibrate it. But so if we have a combination of a scale and a balance, and ideally it would be better if the scale actually shows Newton. And so because if it shows mass, it's just confusing. You could still put them out of sync and then look at the ratio, but it's very confusing for the user. So by knowing the mass, using the balance, and then looking how much Newton force there is at a fixed elevation, a fixed location, then you can basically distinguish what material things are made of. Here I have erbium and many different elements, and bismuth, and yeah, sulfur, lithium. So I did experiments with all of these materials, and they line up pretty well with the expectation. So basically, normally when you want to know the material of something, you have to buy a very expensive, like 2,000 US dollar material analyzer, and it will only analyze the material on the surface. And the very professional ones, they're huge machines, and they take like 10 or 20 minutes to analyze. And here it would be in a second, basically. Now, there are fast ones which are handheld but extremely expensive, and they only analyze the surface. But if you use this scale balance combination, then you can do it in a second, basically.
Wow, that's marvelous.
Yeah. So, but if you use any currently available scale, first of all, it shows mass and not Newton, which is it's very non-intuitive. And secondly, it's not precise enough. So the most precise scale, not balance. Balances can be extremely precise, but a normal scale only has a diamond scale has a resolution of 0.001 gram. Doesn't get more precise. but a scale is based on load cells, and class A load cells, they would be able to reach a precision of 0.0001 gram, and that would be good enough. Yeah. So that would be a resolution of 0.000001 Newton. So
Okay.
it's a resolution I need, because right now I can show with my scale balance experiments, I can show that they've roughly follow the expectation, but they follow it like that. And that's too chaotic to distinguish elements which are close together on the periodic table.
Amazing. Amazing.
Thank you.
Fantastic. So that's the Kickstarter is started to sort of so that you can have that equipment to be able to solve those questions, right?
Yeah, well, I have various sponsors. I have one in China, and yeah, in Hong Kong, and in Swiss. And my current sponsor, he basically supports me with he buys me some equipment, some I have to buy by myself, but basically I get a salary. And
sure, but I mean the goal of the quick starter is basically is what specifically is what would
yeah,
what is the goal?
to build I need to approach a factory to basically produce this scale balance combination, and it will be one device. The scale will be mounted on the balance, and there will be a computer that analyzes the output of both of them, and so there will be one display, not two displays. Yeah. Yeah, everything has to be automatic, and G values will be obtained from online, and the scale has to have a wireless connection to the computer, because you cannot put a wire on it while it's mounted on top of the balance, because yeah, it's like if you weigh yourself, you cannot hold onto something, because that will make the value very inaccurate. Yeah.
Oh, of course. So you had a question there or something there, Jess?
Oh, so are you going to be filing like a patent for that, or is it any like a utility patent, or for the
Yeah.
material anyway?
Not so far, but yeah, I might apply for a patent. Yeah. By the way, the last I did one Kickstarter before, but it reached 1 million Hong Kong dollar, but it was the target value, the target amount was set too high, so I didn't get that money. And I put a bit too many different things in there, because there's also another technology which is much more difficult to achieve, and much more fantastic. That's artificial gravity in space, like in Star Trek, where they can walk around. Yeah. Which I always thought shouldn't be possible, but actually it would be possible. If you can increase the mass without increasing the number of particles, then you have less gravity per kilogram. And you can do that by particle accelerators. They inflate mass. And so if all the walls of the spaceship consist of tiny particle accelerators, where the accelerated stuff has more mass even than the tube, then you could have artificial gravity, because then the spaceship would fall slower than the people inside. And so it falls around Earth, so it's basically falling. That's why we feel weightlessness, not because it's in space, it's because it's in orbit. It's falling, basically. And so then you could walk around in the spaceship. But it's very difficult. You would have to use an extremely dense gas, and it's very difficult to accelerate something close to the speed of light when it's very dense. Usually particle accelerators, they have very little mass that's accelerated.
Yeah, you'd have to have like the advanced containment system or something for that, I guess, right? You'd have to have an advanced containment system for the
yeah, the gas would probably be something like heptafluoride iodine, something like that. The densest gas that you could get in the world. But yeah. Yeah, you would have to prevent it from leaking also, and yeah, accelerating some, because you have to get close to the speed of light for there to be very noticeable mass inflation. Something like 85%, but at 85% the speed of light, the mass doubles. So it's a minimal.
But then it would also require a lot of energy, I guess.
Yeah, yeah, yeah. I guess so.
Well, it's been a great
In
interview so far.
normal particle accelerators, you can keep things inside the particle accelerator for 20 hours or more, but it's a vacuum basically and not a very dense thing.
Mhm. Yeah, I was going to say it's been a great interview so far. I don't know if there's stuff that we haven't covered, subject matter we haven't covered. Jesse, if you had more questions about the specific Kickstarter and the work that Sky's doing on gravity there, that might be useful. But
Yeah,
Oh,
basically the Kickstarter is about about this material analyzer. I call it the chrome gravity scale. Yeah, and so yeah, that's basically it. Yeah, I
where
also
can
did a lot of research about cosmology, about the age of the universe. It's 42 trillion years old according to my theory. But yeah, maybe we can talk
right,
about
yeah, you have the 42 trillion year old cosmology concept.
yeah, which people find a bit funny because 42 is in movies it's famous for this movie what was the name, Guide to the Galaxy. It's a comedy movie about space where there's a giant computer and they ask it what's the meaning of life and everything, and after 1,000 years it gives the answer, and the answer is 42.
Of course. Yeah.
So what is the picture on the
Hitchhiker's
cover of
Guide
the
to the
book?
Galaxy, I think was the name of the movie.
Yeah, Hitchhiker's Guide. That's right.
Yeah, Hitchhiker's Guide.
Mhm.
What does the picture on the cover of the book represent?
Huh?
What does the picture on the cover of the book represent? So what picture behind you?
Yeah, that's in German Elementarräume, which means elementary spaces. And it's basically a graffiti, and there are a lot of circles on it. So if you represent elementary spaces in 2D, you have overlapping circles, different sizes, and you have particles basically always moving on top of these circles, because it's basically just one-dimensional space, but because it's many circles together, you get a feeling for two-dimensionality. Yeah. It's a bit more confusing if you realize that particles are not points but really these spheres, but you still have to represent the impulse basically with a dot. So, because something must be moving on top of those spheres. They go through each other, the spheres. There's no resistance. It's like a superfluid basically.
Right. Interesting. So
Yeah.
Jeremiah, do you have any further final questions?
Oh no, I think it's been absolutely fascinating. And Sky, I commend you on the work you're doing. And I hope the community will find a way to support the work you're doing.
And
Now,
you're
where
doing movies, right? It would be great if I make a science fiction movie, you can act in it.
I'd love to be involved in that there.
Yeah.
I'd like to ask you too also though, now where can people find this Kickstarter? Where do they go to find specifically? And
Yeah, on the Kickstarter website.
and they would
It's not
just
launched. It's not launched yet. It's about to be launched.
yeah. So when it's launched, you'll have a domain on your website, or people will just be able to look your name up at the Kickstarter or the project.
Yeah, I can put it also on my academia.edu account. So you find my academic works at academia.edu.
Yes.
But if you just Google me, Sky Darmos, you will find my academic page very quickly. It should be in the first results.
Okay,
Yeah.
fantastic.
You can also find me on Facebook.
Very good. Well, it's been a pleasure speaking with you and meeting you. I wish you the best with your work. And Jess, do you have any final comments or?
No, it's been a great interview, and it's very interesting. I recommend everybody pick up the book if they want to learn more about SVD.
Thank you. It was nice seeing you in person.
You too.
Yeah, nice to see you.
Okay, be well.
Yeah. Bye-bye. Thank you.
Bye, sir.
Bye.